get started, it would be easier. All right. Hey everyone, welcome to another episode of the Haskell Study Group. I'm your host, Ron Batum with Atlanta Functional Programming. Last week, it's been actually a couple of weeks, we covered and started our talk on functional patterns inside Haskell. What do we mean by functional patterns? We meant, things like passing functions, talking more about arguments and parameters in functions, being able to talk about anonymous functions, some basic stuff on pattern matching, and as well as case expressions, which is a new syntax that we talked about when we were discussing cases inside Haskell. This is kind of what you're seeing here with we ended with this my signum example where we actually implemented a signum function that figures out the sign of a particular value by using the comparison function that's available inside the standard library inside Prelude and writing a different set of cases using case expression syntax. Today we're going to be discussing higher order functions, guards. Guards is a different type of way of defining your functions as well. A little bit more about function composition, which as it relates particular to higher order functions, especially because there's a way of thinking about function composition when we're thinking about higher order functions. And we will end with an idea of the point-free style, just to kind of give you a little bit more detail as to what point-free style means. We've been using it occasionally already in this study group. As usual, as with anything, while I am demonstrating some stuff, I'm going through a couple of resources here. For those of you who are following along in Learn You a Haskell, of course, this is covered, higher order functions especially is covered in chapter, what was it again? It was chapter 7, I think? No, it's chapter 6. Sorry, my apologies. Chapter 6, it goes in and talks about a lot of other concepts, and there's an example from that book that we will be covering, which I thought was pretty cool for higher order functions. When we get to it, for folks who have actually read that book, it'll become clear as to what we're covering. Before we get started on the material, just a couple of announcements. Just as usual, Atlanta Functional Programming is looking for speakers. For those of you who are in the Atlanta area, please feel free to ping either me or Judd. I'm available as Bugram on functionalprogramming.slack. I'm also available in the Lisp Discord server for folks who are there and hanging out in the Lisp Discord server. Just feel free to drop me a line, say, hey, I have this idea for a talk. And this is not include. This is also a shout out for folks who are willing to give virtual presentations too. Atlanta Functional Programming does not discriminate on the person giving the talk and where they're giving the talk. I mean, we'd like to have as many speakers as possible. So drop us a line, get us your talk topic, and we will certainly put it on the schedule. Additionally, as we're continuing on our Haskell journey through this study group, if there's a particular library and or framework that you would like us to cover or at least talk about because you think it's really cool, because all of us here are learning the language and its ecosystem together, feel free to give us that suggestion too, either in the YouTube comments or if you are on those Slack avenues I mentioned earlier, feel free to mention it to us there as well, and we will certainly add those to the agenda. I will point out that we will not start covering any major libraries just yet until we kind of finish off this book and our overviews of Haskell in general, but we will get that as soon as we can. Let me just make sure I'm set up here. All right. So, higher order functions. What exactly is a higher order function? Well, we've actually used the concept of higher order functions before in various shapes or forms just by using some of the functionality that's available to us inside Haskell. But we never really clearly defined what a higher order function is immediately. I mean, we kind of briefly mentioned it when we covered the lambda calculus, and we mentioned that you could pass in a function has a parameter to another function. In fact, if you start looking at currying functions, if you think about it, a curried function is nothing more than a higher order function where the first argument is a value that you need to bind to, a variable that you need to bind to, all right, of some type. And the second argument is a function of the remaining arguments, all right. So that's actually how currying actually works. You can actually see that in our syntax when we talk about currying. When we wrote our notation of the syntax, okay, so like if we wrote our myAdd standard and we take in two integers and you return integers, one way of thinking of this is one way of thinking of this is this is a curried function of two arguments that is passing along. But another way of actually thinking about this is, if we actually go to it, is the first argument is a function, and the second, what it's returning is another function that takes in another argument and returns an integer. All right. So in this case, we're adding two integers together. All right. I'm not using generic type variables here, just just to make it easier to talk about. Just to talk about some of the function stuff here. But you could clearly see, for folks who are watching, that this could be written as another higher order function, because this itself is, especially if you do partial application, it's going to return a function as a parameter. Which kind of brings us to what is a higher order function in general, like a general definition. If you look at a lot of functional programming literature, a higher order function is nothing more than a function that either returns a function has a return value, or it takes a function has a parameter. All right. Folks who are coming in from other languages, you probably are familiar with the most recognizable high order function, say like map or reduce, where they take in a collection and a set of arguments, and they can either, in the case of map, generate and transform a function to, well, it'll transform each element in the list into a new list. And we're going to go and touch base on that in just a minute. Or in the case of reduce, it's going to apply the summation value, or the function that's passed in to the reduction function to the list with the initial element, and then give you some sort of final result. Both of those are higher order functions because, based on the definition, those are nothing more than functions that are taking in a function has a parameter. All right. This is a big thing that I know it's been around for such a long time, and it's been incorporated into a lot of different languages that it's often overlooked, but it's a very big deal because it is another way of actually doing code reuse that, for the longest time, up until maybe even the early 2000s, I would say, in many respects, for folks even coming in from the C world, where you could technically quote-unquote mimic the idea, but it isn't as parameterized using a function pointer. The technique has been been lost, all right, actually taking in functions as parameters or even returning functions as values. And part of it is really because of syntax errors, some errors related to optimizations that could have been done in the compiler, and just various other limitations in the programming languages that needed to be dealt with in order to implement them properly in those languages and maintain the same semantics in it. But for Haskell, from the get-go, because of its staunch position that functional programming should be pushed to the forefront and should be the default paradigm to program, having first-class functions really enabled them to really create a clean implementation of this particular feature, and we'll see some examples of this. The simplest one, higher-order function that's available at our disposal in the Prelude, actually, is a function that most people aren't. I mean, there might be some situations it's pretty useful to use, but you have to figure out what situations this is going to be useful for you. This is the function called flip. Okay, flip is a function that takes in a function, and all it does is it's a curried function of two arguments. And what it does is it returns a new function that just flips the arguments. So if you have a function that takes in a type variable A and returns a curried function that takes in a type variable B to return a C, it just then flips the argument so that you first be able to take a B and then return a function that takes in an A. Sometimes this is necessary if you are especially dealing with matching type signatures so that all the signatures kind of line up and the types all line up. Remember and recall that function application is right associative, so sometimes the return value or the input of another function that you're getting is actually like the second argument of the function that you're dealing with. So flipping the function would allow you to still be able to use the same function for different cases, depending upon which data item you're getting in first. So one example of this is if we create, say, I think probably the simplest one is not dealing with a commutative operation. Let's say that following this is from in chapter 6 of the Haskell book. Sorry, not chapter 6, chapter 7 of the Haskell book. We can define a function using flip that's not even partially applied, all right? This is just taking in the normal type signature that we know of for our minus operator, which takes in, two values of the same type and returns a new version of the type, and we're going to just flip the arguments. So although these all look the same, it'll look like they're taking in the same names, you'll see that the order in which that they're going to apply changes, right? So so normally if you want to use this, in prefix syntax, if you do 10-1, you'll get 9, all right? But if we go and say we flip the arguments, okay, and you pass in the same arguments here, you'll see that 10 is going to be applied to the second argument, and 1 is going to be applied to the first argument of the minus operator, and what you'll actually get is 1 minus 10, not 10 minus 1. All right. So flipping the arguments actually gives you this different behavior. All right. But the main thing to note is this is taking in a function as an argument, and it returned a new function that just simply changes the definition slightly. And we did not have to rewrite f sub to deal with this secondary case. We just were able to use this essentially swapping functionality that's available in the Prelude to create a new function. Right? This should become, in my opinion, a very important tool that you should keep in your tool belt, because higher order functions as you can clearly see here, allows you to create essentially, and the closest analogy that I can come to is for folks coming from the object-oriented programming world, all right? Especially if you're dealing with cases where you don't need to maintain some sort of state in the function object in the callable. This technique is similar to the template pattern that many of you may be familiar with. Okay, so just like the template pattern, this in design patterns, this technique allows you to essentially take pieces of functionality, the skeleton of what you will of a generic algorithm, and you can pass in the pieces that need to be changed as function arguments. And with first-class functions, now you'd be able to then, create a class of algorithms that have the same template using just one with a very minimal code. All right, and especially with anonymous functions, this technique gives you the ability to create one-liners and have all that logic right at the place that the function is being invoked, and not necessarily requiring the developer to actually go in and dig into the implementation to figure out how certain things work, which gives you some benefits as well. We can actually implement myFlip in two different using anonymous syntax as well, and it doesn't really make no difference. All right, if you think about how myFlip is set up, okay, I'm pretty sure that the prelude, this matches essentially what the prelude does for us in right now as it's implemented. I'm just giving you the original signature here. It takes a function and two values, and then you're just flipping the function. You can actually do the same syntax using anonymous. So again, it's going to be the same signature. Let me go ahead and map that signature because it's going to be the same one. But what we'll do is we actually go in and take in a function and create a new anonymous function that takes in those values and just flips the arguments. All right. And we get both syntaxes being the same. Okay. This basically is trying to illustrate that the function declaration syntax for, especially when you're dealing with higher order functions, don't necessarily change regardless of whether or not you're dealing with anonymous functions or you're dealing with normal functions as well. Okay. One thing to really be careful of, and I think this is really dependent upon folks coming in for high order functions from other languages, especially, is parenthesization of a function signature, especially, really affect how the high order function is going to be defined. We've seen this kind of in this case here with myAdd. Okay, notice how we actually parenthesize the second argument. Remember that the arrow operator is right associative, all right, and it requires you to apply the input to the output in this order. If we were to say, for example, change this, okay, to this, we've essentially changed the semantics of the function. Number one, we essentially said that myAdd requires a single argument, okay, which is itself a function, and it's going to return some sort of integer for us. Okay, that's not what you want to deal with when you're passing in and you're creating these higher order functions. Another example, and I think this will probably be better, comes from, again, the reference is in Chapter 7 on return last. For folks who are familiar with return, I think last is available, right? No, it's not. Okay, so we can actually do this. Okay, so this is from Chapter 7 on higher order functions in the Haskell book. This is going to take in a function that essentially going to return the last argument that was provided. Okay, it's going to take in 4 arguments. Okay, A, B, C, D, and it's going to return the last argument. Okay, and obviously for folks remembering, we have this wildcard syntax that we can ignore the other 4 arguments and take the last argument, bind it to some variable, and just return it. Okay, so we have our function here. If we parenthesize this, again, remember how parentheses would work. We'd have to parenthesize because it's a curried function. The arrow operator right associative, you have to parenthesize the following way. So we curry B and then return a function that takes a C. Okay. Then we curry the C and we return a function that takes a D, and then we're returning D. Okay, so now what you're looking at is a function that has the 4 arguments. Each time we're returning a new function that takes the remaining arguments. Okay, if we were to do what I did earlier with the myAdd function and change this and do this instead, again, you will see that, and in fact, let's do it even further. Let's start with an inner function that returns a B, then it returns a C, then it returns a D. Immediately, you will see that there's an error, okay? This error is telling us, if we actually go and look at it, that the type variable of the last function, it's not actually a D. Instead, what it's doing is, the issue it's complaining about is this function itself is the first argument of the function signature that and it's being ignored. Okay, so this implementation, because we changed the function signature ultimately to take in the first argument as being a function itself, is now incorrect. Okay, we've defined a function that takes in 3 arguments and returns a 4th argument instead of a function that takes in 4th arguments and returning the last 4 arguments, and you can see that right here. We've actually did something worse. This first function here is not going to be itself a function necessarily, even though it's a generic type variable, B. It could be a value, which itself is going to cause other problems as well. But the main reason why this is complaining is because the first argument in the return last type signature is a function when it's written this way instead of what I showed earlier, which is this, a function that takes in an argument and returns an additional function. All right. Okay, so we have a couple of questions here. One question, sure, myFlip anon is correct. Well, yes, we could try that. I'm pretty sure that it's correct. Shift, let's do this. F sub anon equals myFlip anon minus. Did I change something here? Variable not in scope. Hold on. Oh, I think I may have forgotten to recompile everything. Okay, there we go. My apologies. Once I changed the function signature, I forgot to recompile. So now let's do this. F sub also is my flip. Let's do a flip here. So f sub, we know if we do 10-1, we get -9. If we do f sub anon, 10-1, we get -9. So yeah, that's correct. So the second question, could we do return last arrow D? No, we cannot. Okay, so the question is could we actually go and change this? Well, let's try it out, okay? If we did this, okay, change this from there. Okay, and if we change this to being this, you're going to see clearly that it's going to still complain because it's not a function of two arguments. Okay, this is a single argument. So return last, by changing it to this syntax, to this type, sorry, not syntax, this type signature, we've ultimately said return last requires only one argument. And that argument is going to be a function that will ultimately return D. So ultimately, you would have to do something like this. But this is not what you want. What you really want is return F, and then have F take in no arguments and return D. Okay, that's not what we want here. Okay, so we're gonna change this back. Okay, now we're good. Other questions? Okay. So I'm going to implement a couple of other types of higher order functions. Again, we've actually done a couple of them already before, but I'm just going to do this as a quick review. Higher order functions can come in many formats inside inside Haskell. Sorry, I'm having a little bit of a brain fart here. The first case is function factories. All right, this is the simplest one. Okay, function factories are just nothing more than methods that essentially return functions, has return values. Okay, the best one to think of is probably makeAdder. All right, makeAdder is a standard function that I tend to write a lot to partially apply the add to take in a value. This is something I use for illustrative purposes. And again, this is a function that takes in an integer and returns a function that takes in an integer and another integer. Okay, and makeAdder is really nothing more than you doing partial application. All right. And it partially applies a function, the value of the plus. So we would end up just doing, plus x, and you end up getting a function that literally can be used to create other functions. So we can create a double function now by just saying makeAdder 2, and now we can do double 2, and we get 4. Really, it's, let me actually change this guy. This is actually not double, this is add 2. Add 2 is the makeAdder. Because doubling means we're actually adding it to itself, which is not what we're doing here. Or if we wanted to do add 3, we could do makeAdder 3, and it's the same idea. Add 3, 2, 5, add 3, 3, 6, and so forth. And you could do the same thing when you're trying to make generic functions for other cases here. Function factories are a very common use case to actually go and do partial application, just to make it easier to when you're reading in the code, to knowing what exactly your you're performing the operation. Yeah, of course, some of the code is very obvious when you're doing partial application, but if you're creating your own functions with multiple arguments, it's easier just to go and create a function factory if you're going to allow partial application for your function. All right. And this can be any function. We can make this a generic partial application as well. Although that's already built in, I would not necessarily want you to go and recreate some of that stuff. But, you know, another idea that comes in mind is also, you know, your standard transformation function here. Second case of high order functions, simple transformation functions. And we've actually seen this with, although I don't know if it's called map here. It might. I think map is the function that I'm thinking of. Yes, this is it. So we all know what map is. Map basically takes in, say, a anonymous function that transforms some value and a list. And what it does is it returns essentially a new list with that function applied to each element in that list. We could write this very, very quickly, actually, using pattern matching in our REPL here. Sorry, in our interactive thing here. First, we need to obviously write our signature. Here, we're going to go ahead and do this same signature. Now, there are two cases that you need to think of, right? The first case is obviously the empty case. So my map f on the empty set. And here, this is going to be just nothing more than the empty list, okay? We're not going to apply anything onto this. But if we do my map f x colon s's, this is the pattern matching syntax where you want to grab the cons syntax, where you want to grab the first element of the list and then separate it from the cutter, the rest of the list. Here, you can just go ahead and do, if I remember correctly, the syntax, and I hope I don't mess this up. It is just, 1 second. I think it is cons. T cons. Cons not look here. Do I have to import? Import list. Where is that? It was. So I think I could just go ahead and do this. I think we could just do gcons. Import data dot list. That's what I need. Now I could do cons, right? There's no cons here. Interesting. But I saw that in Google earlier, but I could just use. Let me see what I can do similar for it. Cons. We'll see if this syntax works. I know the shorthand, but should maybe work. So we do f of x colon, which is the cons operator, my map f on the x's. That should work. Okay, it looks like that's the work. So this, I didn't want to show this syntax up front, but this is the shorthand for the this is shorthand for consing two elements. But I was expecting that that there was actually the cons function, so I can actually show you the cons definition, but that's fine. Let's see this. So now we have our map. You can see that if we do this, we map x times 2, and we pass in, oh, hold on. I see a warning here. Yeah, we don't need this here. Okay, now we're good. And if we pass in 1, 2, 3, 4, 5, we get the same function there. Okay, there's a comment about my code. I think you do not need to explicate my map in the call. I think you... So it's a recursive call, right? So how would it know that it needs to go back into the top level? Of my map. It is required, right? Yeah, that's what I thought. It is required. That's how you define a recursive function, right? So it's going to... So the way pattern matching, again, works is the call is... the actual function call that does the pattern matching for this pattern matching syntax here is actually looking at this argument to figure out which set of rules it needs to go and look up to figure out which pattern should it actually satisfy and actually use in terms of the execution. First off, so there was a comment about, I thought f was passed in at the top level and would be passed in internal calls. While that may certainly sound like a great idea, I actually think for recursive calls, the notation that I'm using would be far more readable. So even if a programming language would encourage that kind of thing, it would be very difficult to know that you're making an explicit recursive function unless there's some sort of indication. I think the easiest way is just calling the function again itself. So I'm not at all dismissing the idea. I'm just merely telling you my own personal preference. If other folks have great ideas, please let me know. Or if they think that I'm being dumb about it, let me know about that as well. In a similar light, I thought to implement this, we go ahead and implement another one that honestly that I thought would be pretty fun. This example comes from actually Learn You Haskell, Chapter 6. Reference is Learn You a Haskell, Chapter 6. And this is an example of a high-order function that is pretty neat. It's a zip width. It's basically a function that's available in the standard library that basically takes in two lists and it combines them. The exact definition is it combines those two lists by applying the function to them. So if you go into Google, zip width basically is a generalized zip. It takes in a function, has an argument, and it applies that function to the tuple and creating a new in general, so basically, instead of creating a tuple, it will apply the function to that to those two lists and creates a new list. So think of zip width kind of like a function that that allows you to essentially do what would be generic, what you would normally have to loop for to loop through two different lists, but it does it in a single iteration. So an example of this is if you want to add two lists together, you could just simply use zip with, do 1, 2, 3, 4, 5, 6, and you'll get 5, 7, 9. Okay. We're going to implement this guy. It's a pretty useful function, especially for those of us who are doing aggregations. It's very useful in the world of data science, certainly. This function is a pretty quick one. If you actually look at, if we just go ahead and adopt it here. Again, the type signature is that it takes in a function as the first argument. And again, this function is going to be a function of two arguments because it's going to be returning us a function that takes in the first list and then the second list and then returns us the resulting list, which may be of a different type. All right. And our standard rules here is going to be the same because zipwith is going to be working on two different lists. We need to write the base case for those two different lists. Well, they may be uneven, all right? And what I mean by uneven is you might get a case like here, 1, 2, 3, and then 1, 2, and you can see that we've only returned and we terminated the execution after only flattening the two elements, and we ignored the third, right? So we're going to be doing something similar here. Obviously, that means we're going to have to use our, check both cases. The first element of the list. Remember, this is 3 arguments, okay? Function, first list, second list. So since we're not actually applying any sort of transformation, we can actually ignore the function at hand, and then we're only dealing with the arguments themselves. In the final case, obviously, we're going to be dealing with all 3. We're going to be dealing with the non-empty first list and the non-empty second list, okay? And in here, we're going to be using, again, the list operator, the cons operator here, to actually do this. We take in, we apply the function, that's our head of our list, and then, I didn't realize that I could do this without parentheses, but that makes sense. Here, we're going to go ahead and, call zipwith on the remaining arguments, okay? So this is the same idea before. Especially when you're dealing with collections, you're going to be ultimately starting with the first element and then making a recursive call in a tail recursive way. This will essentially now apply the same sort of functionality that we've seen before. So if we go and go ahead and run this, and we pass in our 1, 2, 3, 4, 5, 6, you'll see that we'll get 5, 7, 9 in the first case. If we go ahead and pass in here a shorter list, and it doesn't matter which order we do it, you'll still end up getting the short list determining what the terminating condition is. In both cases, notice the pattern in terms of using this higher order function and applying this higher order function, okay? Both of these transformation functions. It's taking the f, right? It has a first argument, or has an argument in general, okay? It doesn't necessarily have to be the first argument. And then it uses that as the basis of the implementation of the actual algorithm that you're building in, okay? This is a particularly useful pattern to start adopting because you can see you can write products, you could write transformation functions for database records coming in, you could do a lot of different sort of transformations just by adopting the fact that, oh, wait a second, these are all following the same sort of template set of steps. Let's just go ahead and deal with that template set of steps, okay? And then we can act accordingly. The Haskell book actually gave an example of using this for dispatching based on using a comparator. The example that it provided is essentially like, let's say that you're writing an employee application that you are, you know, you are defining like some sort of hierarchy for it, okay? Um, and you want to use a different comparator, all right, to determine who the boss is. You can certainly write code for this to leverage this using a complex data type, but at the same time, you can also write a function that says, well, you know, I want to determine that comparison not implicitly by defining it in my data type, which you could certainly do so using the ordering type class. Instead, I could certainly pass in a function to this, and then have my own rules on what the hierarchy is in, because different organizations especially have different hierarchical rules. Okay. Regardless, it is a function that's going to be determining what the hierarchy is going to be. To illustrate this, I think I would defer to you guys checking out and playing around with that particular example, because it's I'd rather not actually go through and implement it here, because it's quite a bit of code related to adding a case expression. But I will say that it's very much similar to what we were seeing here in the transformation case. The only difference is now you're dealing with a custom data type that you've written yourself, rather than using a built-in, which is what I'm using right now, a built-in data type. Okay. Are there questions on higher order functions? This is probably pretty straightforward for those of you who have been using high order functions in other programming languages. So I'm sure this is going to be a quick review, but you know, I'm opening the floor to some questions. Okay, so the next topic that we're going to be talking about is guards. In order for me to do that, I need to discuss what a guard actually is in terms of what we've seen so far. So up until now, in a lot of cases, we've been dealing with conditional dispatch the following ways. Okay, when we're dealing with conditional dispatch, we were either using, up until now, either if then else's, and we've seen an example of this. I will write one down. The simplest example of this, and let me go ahead and share. In order for me to do this, I'm going to probably have to switch over to my my terminal here. Give me just 1 second. This software has go to okay. Okay, and all right. Let me go ahead and share my screen here with folks. Quick question here. Can we pass functions to calculate functions in Haskell? Could you be more specific to that question? It sounds like it's a generalization of the function factory idea that I just demoed earlier, that I illustrated earlier. Could you be more specific about that? Can we use past functions to calculate functions? So the easiest way I could think of your question, because you mentioned like def macro, is the case where you have, like, say, a function with multiple arguments, and you are essentially thinking of creating something like apply, where you take f and whatever arguments that are passed into apply, which itself is a higher order function, and you apply f to those arguments. I would think that you can. It does not sound like something. I think the way Haskell addresses that specifically is much in the same way that you're looking at right now in terms of taking in two functions as arguments, and then a variable, and then changing the implementation internally as a rule, as you've seen earlier with our flip example. In this case, it can certainly be used to create and compute a new function of a different type with different semantics. Yeah. So there was a comment here about how my apply can be used to compute other functions in a point-free style. When we touch point-free, I will bring up this comment, this particular point, because I think in order for us to talk about it, we need to talk about point-free in a little bit more detail than what we've dealt with in past episodes. But it's a similar idea. You could certainly use Haskell's already defined function syntax to create and compute functions. You're not generating functions like a def macro, where you're taking in code and reconstructing a bunch of code, because again, that's a transformation. That's a code transformation. Okay, that's not you're not computing a new function there. Okay, you're computing almost sections of whole code that will be recompiled and regenerated. Whereas with functions, once you're using the pure lambda calculus, it's going to be dealing with applications or composition. So those are the two techniques that you have at your disposal to actually create new functions or even applying a function to certain arguments. Does that make sense? Remember, Haskell itself is a realization of the lambda calculus in a lot of ways. All right, it tries to be as close to the lambda calculus as much. And in lambda calculus, you have in pure lambda especially, you have at your disposal either composition or application. And again, we'll touch base on point free in just a minute. I know the discussion is moving towards point free, but there's a couple of other topics I need to cover before I can cover point free. To be quite honest, so let's just quickly go through those. I'm gonna breeze through these very easily, just because these are stuff that it's not really rocket science, honestly. So the first thing that I wanted to show is, let me just share my, stop this here for a second, share my terminal window here. And let's go back to this and share this guy. Okay. So if you recall in previous discussions, we could use the if-else statement in many ways. We can use to create essentially a conditional branch. Okay, if-else's some folks may consider are types of guards, but they're not guards in the definition of what Haskell deals with. A guard is essentially the idea that you have potentially multiple rules, multiple dispatches that you want to write. Think of it like defining a step function inside mathematics. Okay, that's what a guard is. To illustrate this is we have this, if else that we have at our disposal inside Haskell, and we can use that to actually go and print out some stuff. But you can also leverage block syntax to actually deal with this as well, which might make it look like that you are dealing with guards too. But you are actually not dealing with guards here. You're writing an expression that is computing at the time that it's being evaluated a particular function. All right, and we've actually seen this when we were talking about absolute value. Absolute value, if you recall, is nothing more than a simple example of a guard, right? It's basically a function that takes in an integer and returns an integer. And this guy here, obviously, I can't write this. If I write this, this is going to complain that it's not been defined. So I'll just comment it. And if we go ahead and take in this value, we can use if-else expressions, because these are expressions. They're not actually being computed, to go ahead and, write our absolute value for this guy. Okay, so if we have -5, it's also going to be 5. But we can also write this guy using guards. So a guard syntax is slightly different than the normal if-else syntax that you've seen up until now. Okay, we can still get the same type signature, so I'm going to call this my abs guard just so that I don't have to restart my REPL. And my abs guard is going to take in an argument, but remember, in normal function declaration, in normal function rule definition syntax, you have to provide an equal sign here and then put some sort of rule. Instead of doing this, if we're going to use guards, what you do is you hit enter and you provide instead a, looks like I can't do that here. Let me see if I can do it. Okay, I know what I have to do. We have to use block syntax. So my apps guard is going to be integer, arrow integer. Okay, and my apps guard x is going to be, it's going to have a pipe syntax. I'm going to add 2 spaces here to make it easier. And this pipe syntax is going to be rule equals execution, okay? So in this case, it's going to take our argument, and it's going to allow us to write the rules all in one simple statement, okay? So here we have if x is less than 0, we're going to go ahead and do minus x. And then for all default cases, there's this otherwise clause that allows, say, for all other cases that are falling through, go ahead and execute this particular piece of code, okay? And by doing this, we now have this my apps guard that essentially does what we had before. If we do -5, it's going to return 5. And if we go ahead and pass in 5, it's going to do that as well. Obviously, having these 2 syntax, this particular piece of code, you might seem to think that, oh, well, wait a minute, this does not really make, doesn't really show, you know, the usefulness of, I mean, this is no more different than the if else. In fact, I would say that the if else for this simple case might be a little bit clearer. But if you recall, we actually had our mySignum function that we wrote with a case statement, okay? To recall this, it was basically a signum that takes in an integer and returns a it was an ordering, sorry. It was an integer and it returns an integer, okay? And what this was is mySignum x equals case compare x and 0 of, and we had three cases here. We had GT, okay, if it's greater than 0, then it's 1. If it's less than 0, it's minus 1. And then if it was EQ, it is 0. Okay. Standard signum function. Did I forget something here? Oh, indentation. I have to actually put the indentation in here. Let me go ahead and do that. Sorry. Apologies. Do that. Greater than 1, less than minus 1, EQ 0. Okay. And remember, if we do this mySignum here of, say, 5, we get minus, and we say it's positive. If we get minus 5, we see that it's negative, and so forth. Okay. You could also write this guy using, without actually using the comparison operator, by doing what we had before. Okay, and has a three sets of statements. So we could do mySignum guard, which again takes in integer, okay, and here we write mySignum guard and takes in a value, and remember we have to use the pipe syntax. So we go ahead and use the pipe syntax. If x is less than 0, it's going to be minus 1. If x is greater than 0, it's going to be 1. And we have our otherwise, which is going to be obviously the equal case, and it's going to be 0, and we can just go ahead and write it like this. And we get the same sort of behavior that we had before. mySignum guards will give us positive if we gave a positive number, and a negative if we give us a negative number as well. Notice the syntax difference, okay? The case comparison expression and the guard syntax look fairly similar, but you are writing essentially kind of like a switch when you're using guard syntax. At least for me, when I'm looking at this is kind of how I kind of interpreted this particular expression. And what it does is allows you to group together your cases into a single, block-like syntax, especially. And if you're really dispatching on, one or more things, you don't have a fairly complicated situation action sort of rule. It'd probably be easier to leverage this. If you're doing more complicated logic, it might be better to return, say, an ordering and then write some rules and leverage pattern matching to dispatch on the appropriate rule. That's another way of also handling it. But guards gives you this ability to essentially group conditions together and make your rules look more concise. All right. And again, for folks coming from the mathematics world, this looks fairly close, like step function syntax, where different parts of the range of a given set will have a particular function applied to those values. All right. So this guard syntax, I would say, is very close in nature to that particular mechanism that you've gotten from mathematics. Questions on guards. It's really not more complicated, but it's so up until now, when we were talking about higher order functions, we never really I mentioned it earlier, but I really didn't discuss it. We mentioned that function composition is itself is a kind of a higher order function. Okay, it takes in, remember, two arguments, and what it's returning is nothing more than a new function. Okay, it's a function factory. All right. If we actually look at the type signature of the dot operator, you can actually see this clearly in the dot operator syntax. Okay, sorry, the dot operator type signature. It's taking in a function that returns a b to c and a function that takes an a to b, and it'll return a function that goes from a to c. Okay, with all the type variables obviously aligned. So that means if if you do f dot g, that means g must be returning a function from a to b, and f is going from b to c. So it will go ahead and return something that goes from a to c as well, f of g of x. This is particularly useful to know, just because it allows us to actually understand the composition operator and how it actually fits in the overall framework that we have inside of Haskell as well. Okay, remember, all these are polymorphic arguments inside of our function signature. Well, given that, hold on 1 second, I'm looking at my notes here. Right down here. Right. Okay. Okay. So one way of thinking of the composition operator is kind of like in Unix world, kind of like pipelining data from the output of one function and the input into the input of another function. Okay, I know this is very familiar for folks who do a lot of data flow programming, where you're kind of piping the data from one operation to another operation to set up kind of basic workflows. One way of actually illustrating this is honestly just looking at a couple of things on top of a list. One example, this comes from chapter 7 from the Haskell book, which I thought was particularly interesting, was the fact that you have a list of numbers, okay, and you want to negate the sum, but you want to apply it on the list of x's. So sum, obviously, for folks who don't remember, it's a function that literally reduces the x's and adds them all together, and obviously negate the dot. This dollar sign, if you recall, is basically preventing us from having to put parentheses around stuff. We could certainly have done negate dot sum of x's and we'll get the same result. But for folks coming from Haskell, once you've used dollar enough, you'll realize that it actually cleans up some of the code, especially when you're starting to do partial application in the process of composing a new function. All right. So that's why I'm starting to use dollar a little bit more. Now, if we look at the evaluation of this, okay, we know what we're ultimately doing. First, we're taking negate. We're breaking it apart, and we're saying negate the sum of x's. This is what the above function does. Okay. Well, this essentially is going to be evaluated to negate 1 through 5, which is 15, and which will give us the final result of minus 15. Since application is higher in terms of precedence from composition in Haskell, application is going to occur before composition occurs. Okay, so what that means is negate is going to actually be applying itself to the result of sum passing into x before negate and sum become their own function object. The only way to really prevent that from happening for folks who are dealing with function composition and they want to create their higher order function, all right, a set of functions all together into the single workflow, is actually assigning this to an object before actually applying it to the data. So what you could do is you could do negate sum is negate sum, okay, and this creates a new function object for us, which with that signature, and now we could just go ahead and call this guy on our x's, and we'll get the same answer. Now this is a single function call. But behind the scenes, it's actually two function calls that are being applied in succession, as many of you know. But that's something to be aware of when you're dealing with higher order functions, and in particular when you're dealing with composed functions. Okay, function application is higher than composition, which means as soon as it hits some sort of data, application is going to execute, and you're going to start getting all the values all together. So in this respect, laziness only is as far as when all variables for a function signature are not bound. All right, you're preventing computation from happening when all your variables are not bound. Once they're all bound, function application is going to start, and you're going to start actually dealing with the results immediately, okay? Because you've essentially gave them all the information to allow the application to occur. We can see a lot of these kinds of things when we're doing composition, because composition is so vital to using and to be used in Haskell. That you're going to see a lot of these combinations of using the dot and dollar syntax in many examples, and you're going to be probably using it in a lot of examples. For example, we have this standard way of doing, getting the first 10 integers, okay? If you wanted to actually say, take 5 after reversing them, you could certainly write take 5 after reversing them, and then apply 10, and it will get you the first, 5 integers after reversing the list. Okay, you'll also be able to do composition by passing in the arguments directly. So instead, for example, if you want to say enum from 3, which is going to give us an infinite list. If you remember what enum from does, enum from basically takes a starting element and then it creates an infinite list. If you want to stop that infinite list and just take the first 10 elements from that list, you could certainly do so. It'll go ahead and generate essentially an iota for you from 3 to whatever element that you asked for, inclusive of the first element. All right. You could also use the dot syntax that we did earlier and do this, and this allows you to also get the same result too as well. This pattern is going to be so useful. A lot of times, some folks tend to label their functions using this composition until they apply, and they need to apply it, so that way they could create different workflows. So if you wanted to take the above workflow, you could certainly make a function that takes in some start point, and then if you pass in the function, you'll get the same result as well. Okay. One of the reasons why this notation is so simple and why it's preferable than the parenthesization is because of the fact that in a lot of examples that you're seeing from code, it's easier to compose two functions using this dot dollar kind of syntax versus using heavy parenthesization, right? You can just keep on going with this application. So like, let's say that we wanted to grab the first 10 integers, double them. So let's go ahead and, create a double function, okay? Okay, now let's take 10 of double of enum from, and we start from 1. You could see that you could write this high order workflow, and I call it a workflow just because it is a high order function, it is being composition, but you are essentially building up the function until you're actually getting the data, right? So in this case, we're getting the data with the starting point of 1. You could see that, did I mess something up here? Got it. I think the reason is because I need to do my map double, because that is a list. Double is taking a value. Map double from. Another way of doing it is also someone suggested also to use. You could also change the ordering here because of the fact that I'm actually grabbing only a finite number of this list. You could also do this, and you get the same result. So thank you for that. Point is you're building up these higher order functions, these workflows, and then once you get this terminator, okay, your data that can be bound to the final variable that invokes the application, then everything starts off. This is kind of the basis of a lot of the lazy evaluation workflows that you would encounter when you're writing Haskell code, or even functional code that allows composition in other languages too as well. I'm mentioning other languages briefly here just because of the fact that folks are using this. If anything, these techniques that we're providing in Haskell is not specific to Haskell, especially in languages that provide functional features. This is number one. It just so happens that Haskell syntax is much cleaner in many respects to adopt some of these things. So that's something to be aware of, and that's something to appreciate. You can use this to, for example, write your prototypes with types accordingly, and you'll end up being able to adopt them if you're using other languages with slightly more verbose syntax, but you'll end up getting the same idea, and you'll be able to move your Haskell code over into other languages if you need to. All right. This function composition was very important because this operator style of building allows us to essentially write in a point-free style, which is the terse style that we've been discussing earlier in this program. Point-free refers to essentially composing functions without specifying their arguments. Now, that's not entirely true in some cases because of the fact that you're specifying some of them. You don't need to specify all their arguments. Is probably how I would argue what point free is. The point is the point in point free is the arguments that needs to be applied to a particular function. When you're dealing with function application, in partial function application especially, you may be able to take a function that takes in multiple arguments and apply a subset of them to return a function that has the remaining arguments curried, right? And in that case, you are technically applying a function to a point, but I would make the argument that since you don't have all the arguments to complete that function invocation, that makes that still fall into the definition of point-free style. You still are dealing with the only functions at this point, okay? So when you're dealing with point-free style, you're only dealing really with function composition, okay, really, okay? And we're adding more operators or quote-unquote points to be able to drop points or arguments, okay? Point-free style, as you can see in this example with our MyMap example, it actually really creates a terse, tidy, clean thing as to what functions that you're actually dealing with. And it makes a clear distinction in a lot of cases as to what the function is and what the data is, all right? Because you've built up this very high number of functions. That's a big function function itself, and you're just going to apply them in the order in which you've composed them from right to left in order for you to actually build up your final value, your final result, okay? And it stems from this composition that point-free actually becomes very, very useful and very, very clean, all right? How do we actually, though, because we've actually seen examples of creating point-free functions just using existing functions that we leveraged. When we define any function, okay, in a point-free style, okay, we can create functions that can ultimately be the last function that data can be passed in so that application can occur. And we've already seen this with our negate sum example, okay? When we set up the negate sum function, okay, that we did earlier, we did not actually specify any arguments to negate or to sum, okay? We just said that they need to be composed with each other, okay? We basically instructed Haskell to say, you know what, construct a new function from these other functions and apply them in the order in which I provided them from right to left, okay? You could do that with your own functions as well, all right? Let's take an example. Let's take, let's see, I think this one from, yeah, I think this one from, where was it? Okay, we'll do it this way. Let's do a left of our own fold function, okay? This is similar to what's available in Chapter 6. So this example comes from Chapter 6 in Learn You a Haskell, okay? We're going to create our own myFold function, okay? I'm using multi-block syntax here in the REPL because it makes it easier for me to write the signatures as well. And actually, let's call this F. This is going to take us, it's going to be a reduction that takes a starting point, an initial value, and a list of integers, and gives us a final int, okay? Everyone who knows reduction functions knows that if you have a final into there, that's going to be essentially going to reduce itself, okay? And we take in the initial value, and our actual non-empty list, and we go ahead and call fold L on it. Okay. Fold L, if you recall, basically takes in the function that we want to fold on, the initial value, and the x's. Okay. So now we have our function here. Okay. And obviously, if you pass in, what's it? An initial value and a set of integers here, it'll go ahead and call fold. But what if you want to make this into a point-free function? We could certainly do a point-free function of this version by simply applying fold L to just plus. Because we don't need to actually go and provide the function signature, okay? We don't need to provide any of the arguments if we're just building up the function from other existing functions. Instead, we just need to say how do we want to compose them. Like in this case, we're saying fold L is taking the first argument plus. We bound one of the arguments of fold L to an operator, and there's still remaining arguments. And that function is now returned to f, okay? And now we can get the remaining arguments as well for that, and we can actually set that all up. There are other examples that you could build for point free. A lot of them end up just being just combinations of compositions with partial function application. All right, so you could build your let's say that you wanted to grab the length of a list of let's say that we're going to create a count, okay? That's going to be count evens. And what this does is it'll take the length of filter on, hold on, let me just make sure even is still the signature there. Yes, it is. Okay, so even 2 is there. Okay, so we can create count evens, and we will say we're going to grab the length of filter evens, and what this does is going to grab all the even numbers and tell me for in a given list, and just filter them out. Tell me how many instances of an even number occurred in a given list. Okay, so for example, if we call this on say evens of 1 to 10 or 0 to 10, probably easier, you'll see that we're going to get 6 because it's 0, 2, 4, 6, 8, 10. Because 0 to 10, recall, is going to give us 0 and 10 inclusive. Okay. This is one way of building up your functions into a set of core algorithms that you could then just apply to data once you get them at appropriate places. Okay. So that's what I wanted to talk about for point free. Point free is a very simple concept once you really start getting used to it. It is a little jarring for folks coming from other languages, mainly because of the fact that it's actually extremely difficult without some notion of building up these higher order functions using composition to actually illustrate creating these sort of workflows and then waiting until you have the data to actually go and apply them. But I think a lot of languages nowadays are closing in on that gap. I know Python has this ability for you to write composition very cleanly too as well. The only thing is with type classes, Haskell makes things a little bit more safer from a type standpoint, so that you don't have to deal with a lot of the runtime errors that you normally deal with other languages. Okay, any questions? All right. If that's the case, I really don't have any additional stuff to show you guys. There was a section on, talking about, how do we use print and the difference between put-stir and put-stir line and in print. And I think most of you can now see um, uh, from composition in our talk about actual point freestyle that print and a lot of the printing functions are nothing more than a composition of the put stir function, which will return an IO monad, composed with show, which is a type class on the type that you're kind of showing on. Now, once you get enough practice, you're going to start realizing a lot of functions in the Haskell prelude are conveniences for composed functions that are available in the prelude. So, its technique of composition and creating high-order functions is an absolute must to master, because it will really simplify your code. And honestly, it's going to change the way you write code in other languages. So that's it for today. Appreciate everyone taking their time out of their days to watch this walkthrough. Those of you who watch this stream later on, I hope this provides some use to you all. If you guys have any questions and comments, always, please post them in the YouTube video comments, so that way we can look through them accordingly. I hope to see you guys next week, where we start talking more about recursion, which is available in Chapter 8 in the Haskell book, and in Learn You a Haskell, that's covered in Chapter 5. Okay? Until next week, thanks. I'll see you all later.